Alright, so today I'm going to discuss cross-sectional volumes. Now, this involves taking a cross-section that forms some common geometric shape, finding its area, and then adding up a bunch of those through integration. As such, I'd recommend you watch my video on quick integrals if you don't already know how to do that. Now, for example, let's say we have this arbitrary shape that forms the base of this solid. Now, we're also going to take a cross-section of this solid, which we've got there, and this cross-section will form either a square, an isosceles right triangle with the leg as the side, an isosceles right triangle with the hypotenuse as the side, or an equilateral triangle. Now, we technically could also have a circle as a cross-section. However, this is a different, albeit only slightly different, process, but it nevertheless deserves its own video. Here, I will focus on these four main cross-sections, also known as slices. Now, before I get to cross-sections, I'd like to discuss an integration trick of sorts. Now, in the past, whenever I've done integration, I have always had the upper bound be some curve, and the lower bound be the x-axis. However, that is not necessary. If you wanted, you could have the lower bound also be some curve. So, if you wanted to, you could find the area between these two curves, with the upper curve being f of x, and the lower curve being g of x. Now, the way you do this is you would take the integral of f of x, subtract g of x, and do this with respect to x, where f of x is the equation of the upper curve and g of x is the equation of the lower curve. Now, because we are finding area, we need to have limits, because, it's a definite integral. Now, you could arbitrarily set limits here, for example, like a's there and b's there. However, a lot of times they want the limits to be those 2 points. So the way you find those is you simply set f of x equal to g of x, and then solve, and you will get the 2 x coordinates where they intersect. And then you simply set those 2 x coordinates as your a and as your b, and then integrate. Now, as an example, I'm going to find the area between the curves x squared and 2x. 2x and x squared. So, to do that, we will have the integral of 2x, because it's on top, as you see here, minus x squared, and then with respect to x. Now, the first thing we need to do is we need to find where these two intersect to find our limits. So, we'll set them equal to each other, and then we'll subtract the 2 to both sides. We have 0 equals x squared minus 2x. Factor out an x. So now we have x times the quantity x minus 2 equals 0. So this means that x equals either 0 or 2. And that gives us our limits. So we'll integrate from 0 to 2. Now then, getting right into integration, this 2x, that gives us 2x, and then we get x squared over 2. 2's cancel, minus then x cubed over 3, and again, from 2 to 0. So then, plugging in the 2, so we have 2 squared minus 2 cubed over 3, and then subtract that from 0 squared minus 0 cubed over 3. Now, of course, 0 squared minus 0, this all here, that's just 0, so I'm going to just ignore that now. So we now have 4 minus 8 thirds, which is 4 thirds. So, the area between the curves 2x and x squared is 4 thirds. And that is the general process you go through to find the area between two curves. Now, as I mentioned earlier, we are integrating from A to B the infinitesimally thin cross-sectional areas, of course, dx. So what we need to do is we need to find the area of each of those infinitesimally thin cross-sections and essentially add them all up, and we will get our volume. Well, remember that when we're doing, regular integration, two-dimensional, finding areas, not volumes, that we use these infinitesimally thin line segments, which I will label S. Now, S is also the side length of the cross-sections for when we're doing volume. So what we essentially need to do is we need to use S to figure out the area of the cross-sections, and then we can add them all up. Now, also remember that, as this graphic shows, S is equal to f of x minus g of x, or the upper curve minus the lower curve, because, S is height there. Well, you may be asking, well, what if my lower bound is the x-axis, and I just got this upper curve here, whatever, it doesn't really matter. Well, in that case, the equation for this is y equals 0. So, simply plug in 0 for your g of x, and you will get s equals f of x minus 0, or just f of x. So, if you ever have the x-axis as your lower bound, plug in a 0, everything will work out fine. Alright, now the first cross-section we need to figure out the area of is the square, which has side length s here. Now keep in mind it's a square, so these are all s. Now, hopefully you should know this automatically, but we multiply these two sides together, and we find out that the area of a square is s squared. Hopefully this explanation wasn't needed. So that means that the integration formula for cross-sectional squares is the integral from a to b of f of x minus g of x squared, of course, dx. So that will give us the volume for cross-sectional squares. Now, next we have the isosceles right triangle with the leg as the side. So this is S, and that is also S. Now, the area of this, of a triangle, I hope you remember, is base times height, which gives us S squared, times 1/2. As such, the volume for these cross-sections is the integral from a to b of 1/2 times f of x minus g of x squared dx. Now this next one gets a little trickier. Here we need to find the cross-sectional area of an isosceles right triangle with the hypotenuse as the side. Now, as you remember from the previous segment, the area of that was 1/2 times the leg length, or L, squared. So we need to find these leg lengths in terms of S. And to do that, we will use Pythagorean's theorem. So we have S squared equals L squared plus L squared, or 2L squared. Divided 2 to both sides, we have S squared over 2 equals L squared. So we can plug this in for that L squared up there, and we find that the cross-sectional area for an isosceles right triangle with a hypotenuse as a side is equal to 1/4 S squared. So the volume of that is the integral from a to b of 1/4 times the quantity f of x minus g of x squared dx. Now, the last cross-section we need to find the area of is the equilateral triangle. Now, the equation for the area of a triangle is 1/2 base times height. Well, we know the base, we just need to find the height. Now, I'm going to tell you a very poorly kept secret about equilateral triangles, and that is that each of these angles is 60 degrees. And also for equilateral triangles, because it's equilateral, this is also S. Now, this is important because the way we're going to find this height, and the most common way to find the height, is through trigonometry. So we need to take the sine of 60 degrees times s. And that will give us the height. Now we need to multiply by s because sine gives us the opposite, or the height here, over the hypotenuse. So if we multiply it by the hypotenuse, we just get the opposite, which gives us the height. There we go. Now the sine of 60 degrees is square root 3 over 2. This times s, and that gives us our height. As such, the cross-sectional area for an equilateral triangle is equal to square root of 3 over 4 times s squared. Therefore, the volume for the equilateral triangles is the integral from a to b of square root of 3 over 4 times the quantity f of x minus g of x squared, dx. Now, I will give an example to demonstrate this whole process. Now, for the base of the solid, we will use the curves y equals 2x and y equals x squared, as I had used earlier. Now, the cross-sections will be of squares. Now, to set up the integral, we have the integral from 0 to 2, as I've explained earlier, of the quantity 2x minus x squared squared, dx. Now, the first thing we want to do is get rid of this square. So, we'll just go ahead and do that. We have the interval from 0 to 2 again, of course, and then we have 4x squared plus x to the 4th minus 4x cubed, dx. Now, if you don't believe me on this foiling, go ahead, do it for yourself, and you'll see. Now, the next thing we want to do is take care of the integral. So this 4x squared, that's 4/3 x cubed. It's a cube there. And then plus x to the 5th over 5, and then minus 4 over 4x to the 4th. And we'll cancel those 2 fourths. And then that is again, of course, from 0 to 2. Now, we'll plug in the 2 and the 0. So that gives us 4/3 times 2 cubed plus 2 to the 5th over 5 minus 2 to the 4th. And then that minus the quantity, 4/3 times 0 cubed plus 0 to the 5th over 5 minus 0 to the 4th. And this all here is, of course, 0, so I'm just going to go ahead and ignore that right away. Now, 2 cubed is 8, and then times 4, that's 32 over 3, plus 2 to the 5th is 32 over 5, and then minus 2 to the 4th is 16. Now, if you add and subtract all that up, you get 16/15. So that is your answer. Now, if I was using cross-sectional isosceles right triangles with the leg as the side, I would have multiplied this by 1/2. If the hypotenuse was the side, I would multiply this by 1/4. And if I was using equilateral triangles, I would multiply this by square root of 3 over 4. So that is the difference between each of those 4 cross-sections. But nevertheless, hope you enjoyed it, hope you learned something, and see ya.